So I think up to this point we've assigned up to number 24. Does anybody have any questions from homework before we get started on the new stuff? Yeah, Joey.
Number 22.
22? Sure thing. Actually, she's golfing.
Golf is got
Emily.
I wish I golfed instead of soccer. They're two different types.
Yeah,
I like golf.
they're totally different seasons, man. All right. So first thing I would do here is I'm going to graph this thing and take a quick peek to give myself an idea whether I should be shooting for a odd, even, or neither. So if I look at that, that looks odd to me, right? Because like caddy corner are identical. So let's try to do that then. So remember, for odd, we'd need to show that k of negative x is negative k of x. So if I start with k of negative x, I'm going to take my k, and every place there's an x, I'm going to replace it with a negative x. If I simplify this, negative x to the third is just negative x to the third because I have three negatives. And negative 2 times negative x is positive 2x. So there I'm simplified down. Since I'm looking to get to negative k of x, I'm going to factor off the negative. So the negative 3x cubed becomes positive 3x cubed. And the positive 2x becomes negative 2x. And I notice here now that that is exactly k of x. So I'm at negative k of x. And we're donezos. Joey? 24? Sure. So 24 asks to find all the vertical and horizontal asymptotes for the function. Well, I'm going to start by typing this thing in, so I'll clear out what I had in there. I want to type this in exactly as it looks on my calculator, so I need to get that horizontal fraction bar. To do that, I press alpha, y equals, and then pick option 1. Then I don't have to muck around with any parentheses and worry about getting those correct. I can just type it just like it looks like on my sheet of paper. I don't have to think any harder about it. I'll go ahead and graph that now. So when I look at this, I see three asymptotes. I see a vertical asymptote looks like negative 1, negative 2, negative 3 right here. And then I see another one at positive 1, 2, positive 3. And then I see a horizontal one that looks like the x-axis, right? Which is the same as y equals 0. So now what I'll do, now that I've identified these from the graph, I'm going to confirm them with a table, right? So for negative 3, I'll make a xy table. And I'll start by picking some x's that are a little less than negative 3, but get closer and closer to negative 3. and then we'll do some x's that are a little bit bigger than -3, but get closer and closer to -3. So those would be the ones I would choose. Again, you don't have to pick these ones specifically, but this is like neat and systematic, and I don't know, the mathematician in me likes that. What I need to do now is evaluate my g of x at each of these values for x. The easiest way to do that is to use my calculator. So I'm going to retrieve the y1 command from my calculator. To get that, I'm going to press the vars button, which is right here below the down arrow. I'm going to move over to the yvars tab. I'll pick the function option, and there I see my y1. So just like function notation, I'm going to do like y1 of -3.1, and then press enter. Now, rather than jumping through all those menus all over again, what I'll do is just press second and enter, which will recall the last thing that I entered in my calculator, and I can just go back and edit that. And do it again, second and enter, and then edit that. And those are the first three values for my table. So -8.36, -83.36, and -833.36. I notice for each of these, looks like y is getting smaller and smaller and smaller without bound. We're heading to -infinity. Now let's do the next three. So again, I'll press second and enter to recall the last thing I had in there. I'll edit that to put the -2.9 in there, and then press enter. Recall that last thing, added it to -2.99, and then once again to -2.999. So I have 831, 8331, and 83331. Again, all I notice here are getting bigger and bigger without bound. The fact that I have infinities at both spots tells me that what I'm looking at is a vertical asymptote. On to the next one. So again, we'll start setting up the same way. Make myself an XY table. So I'll start with values a little bit less than +3, and then get progressively closer and closer to +3. And then I'll start with values a little bit bigger than 3 that get progressively closer and closer to 3. Once again, I'm going to go ahead and do that second and enter, and I think this time I'm just going to go a little out of order because it's a little less editing, so I'm just going to nix the negative sign and press enter because I got that one already on my list, and then 299, and then 2.9. So I have little out of order I got my terms, but that doesn't really matter. I just need to get them at some point. That's a 3. Come on. There you go. So again, notice we're going to -infinity. Now let's do the other one. Second and enter. So this time I'm just going to edit what I got. 3.1, 3.01, 3.001. So I have 1.80, 16.81, and then 166.81. Again, we're going to +infinity. I take those two, and that tells me that what I have here is a vertical asymptote. Last one to look at is the y equals. Now, for a horizontal asymptote like this, the table's going to look a little bit different, because here what I want to do is look at the y values when the x's get very big or very small. So I'll just pick some progressively smaller and smaller x's and progressively bigger and bigger x's. Again, there's nothing magic about the set of numbers that I'm choosing. You just want them to be getting appropriately bigger. So like a magnitude of 10, but you could have done like -6, 228, -228, and then -7,032 or something. Like, there's nothing wrong with that. But like, just easy to put those into my calculator. Is why I'm using those. So again, doing the same thing, second enter. Gonna enter that in. Oops. Goof that up a little bit. Press enter. Oh, boogers. I got a fraction coming out of that. So what I'm going to do is I'm going to add a little piece to the end of this. I'm going to press the math button and then choose the decimal command. That'll tell the calculator that whatever comes out of this, just give it to me as a decimal. So there's that. Second enter. And now I'm going to do second delete to do the insert. Notice my cursor's changed from flashing black to flashing white. That allows me to just add in the 0 without overwriting anything, so I don't have to, again, go back through all those menus to get that decimal option there. And if I look, each time I'm getting a little bit closer to 0. And now let's go ahead and do the same thing for the positives. Here I'm going to start at the bottom because I don't have to do as many enters, or inserts, I should say. So we got 0.088 and then 0.0098, and then this first one, 9.98. Well, that seems out of place, but look at the end where it says e to the -4 or e -4. That means that's scientific notation on your calculator. So what this number is really 9.98 times 10 to the -4. So that's 3 zeros and then 998. So again, what we're seeing is everything getting closer and closer and closer to 0 there, which is confirming to us that what we see is a horizontal asymptote. Does that feel good, Joey?
Yeah, it's just the last one for 1,000. I plugged it in, and I got like 9.9.
Right, but it has that e -4 at the end.
Yeah.
So that means times 10 to the -4th. That's how they calculate right scientific notation.
Okay.
So you have to move the decimal like 4 places to the left.
Oh.
Yep. So that happened to me also, right? But you just got to keep reading, and you got to see the e -4 at the end. That's how the calculator writes scientific notation. Right? Like if I write 9.98 times 10 to the -4, the calculator writes it this way with that tiny capital E there, which is like, okay, if you say so, calculator, but that's all that means. It's just scientific notation. But we got to be careful about that, right? Because it's easy to not read all the way to the end because you get the 9.98. Okay, good enough. Make sure you read all the way to the end. Especially if it's not what you're expecting, right? Like I would have expected that number, to be smaller than the previous. To get 9.98 there is kind of weird. Okay. Anybody else on homework questions? There's a pretty good assortment of them. You picked some evens, so you got some extra answers that you couldn't check because from the odds, but that's okay. All right, good choices. A little extra feedback never hurt nobody. All right, then today we're going to start with section 1.7, where we're going to look at function operations. So we're going to start with the 4 fundamental operations that you guys have been working on really ever since you started going to school. That being addition, subtraction, multiplication, division, right? When we talk about operations in math class, those are the 4 fundamental basic operations. So that's what we're going to start with. So this says, let f and g be 2 functions with intersecting domains. Then, for all values of x in the domain, the algebraic operations performed on f and g are defined by the following rules. The sum of f and g of x is just f of x plus g of x. You can just add the 2 functions. F minus g of x is just going to be f of x minus g of x. I can just subtract the 2 individual functions. F times g of x is just going to be f of x times g of x. I can just multiply the 2 individual functions. And f divided by g of x is just going to be f of x divided by g of x, provided that g of x is not 0. Why do we have that extra little caveat in there where g of x can't be 0? Because it's in the denominator, right? And we know that we can't divide by 0. So not a lot to say about this. Everything is working exactly as I'd hoped, right? If I add 2 functions, it's just like adding the individual parts of the function, we're done. You know, if I want to subtract, I just subtract them. If I want to multiply, I just multiply them. Works exactly as we'd hope it would. Let's look at some examples to kind of hammer this home. So let's say f of x is the function 2x minus 3. And g of x is the function square root of x plus 2. And we want to do the following. So let's start by doing f plus g of x. From our definition above, that just should be f of x plus g of x. Well, I know in this problem, f of x is 2x minus 3. And I know that g of x is square root of x plus 2. And now the only thing left to do would be to combine like terms and do any kind of simplifying, if there's anything possible. Is there anything to simplify here? Any like terms to combine? No, right? I know that I can't combine the 2x with the x because the x is underneath that radical and the 2x is not, so those couldn't go together. And likewise with the negative 3 and the 2, although those are like terms, one is under the radical, the other isn't, so I know that they can't go together. So that's as good as we can do. We're done. Mr. Kulik, I feel like I didn't even do anything. Well, you didn't really do anything. Okay. So let's try the next one. Again, our definition says f minus g of x is just going to be f of x minus g of x. Oops, that's not the problem though, Mr. Kulik. It was g minus f. Oops-a-daisy. Okay, well, I'll just do this the same way. I'll write down my definition, g of x minus f of x. I'll plug in my value for g and plug in my value for x, just like we did before. Everybody agree that looked good? I wish somebody would have objected because this is wrong. I made a mistake here on purpose because it's a really easy mistake to make, and I would wager that half or more of us would make this mistake even consistently after showing you that this is an easy mistake to make. So here's the mistake. F of x, all of that is negative, correct? So when I write this, I really need to think about it this way, because that negative sign needs to apply to all of f of x, not just its first term. So my actual answer should be square root of x plus 2 minus 2x plus 3. And just like before, there's no like terms to combine, so we're done. Now, that like distribute the negative thing is easy to forget to do. Part of why I intentionally tried to trick you into like doing it without doing it, because it's really easy to do. I want to point this out and make a big deal of it, because if I don't show you this like a bunch of times, everybody will miss it. Even after I show it to you a bunch of times, probably half of you are still going to forget this. I'm trying to take some more time now and try to get that number down to below half by making a big deal out of it right now and saying it over and over and over again. Because the usual teacher philosophy, you say something once, half the people hear it. You say it twice, and then like another half of the half that didn't hear it. It takes a long time before everybody hears it. So that's why I'm sitting here still talking about making sure that we're being careful in the subtraction sense, that we're distributing the negative through the entire thing. Okay, let's do C. This is g times g of x. Well, my definition for above says I can just do g of x times g of x. And I know from my definition that g of x is square root of x plus 2. Now, can I simplify square root of x plus 2 times the square root of x plus 2? Okay, how would I do that? Great, why? Yeah, so remember, like if I have like a times a, that's a squared, right? So this would be like the square root of x plus 2 squared. And we know the squared cancels the square root. And we're left with x plus 2. Everybody's okay there? Fantastic. Already stat for now. Okay, and then our last example. This is f divided by g of x. Well, this is f of x over g of x. And I know f of x is 2x minus 3. And I know g of x is square root of x plus 2. So let's go ahead and use our definition and plug in what the f and g are. Can I simplify that at all? Well, remember back in geometry, you guys had a rule for situations like this, right? What did we say back in geometry? For something that looked kind of like this? It's that we didn't want to leave a radical in the denominator of our fraction, like a square root in the denominator. So squaring a fraction changes the value. That's not what you'd want to do. But let's slow down a bit before talking about like what we did in geometry. In geometry, did you ever have the square root of an algebraic expression, though? Or was it just like the square root of a number? It was always just a number, right? You know, it was like the square root of 5 or the square root of 8 or whatever was like your denominator. So in cases where it's just a number down there, yes, we'd expect you to rationalize that denominator. But in this class, if we have the square root of an algebraic expression, something with an x in it, we're not going to worry about rationalizing the denominator. It's more trouble than it's worth. We're just going to stop right here. Okay? So again, I pick this example because it gives me the opportunity to kind of like talk about when we're going to do this thing that we did in geometry and when we're going to skip it. So as long as like the square root has an x in it, we're just going to skip it. That's as good as that's all I would expect. If you did go ahead and rationalize the denominator by multiplying the top and bottom by root x plus 2 over root x plus 2, it's fine. I'm not going to mark it wrong, but you're doing more than you need to. Everybody happy so far? Again, this should be pretty easy, right? This feels pretty easy. There's a fifth operation that we define on functions. Does anybody remember this? This would have been something you would have talked about last year in your Algebra 2 course. A fifth operation we can do on functions starts with the letter C. It's called composition. So what does composition of two functions mean? Okay. So if f and g are two functions such that the domain of f intersects the range of g, we say the composition of f, okay. The composition f of g, which is denoted as with this symbol here, is defined as f of g of x. So little pet peeve for Mr. Kulik. When you read this, this is read as f compose g. It's not a word. Please don't say fog. It drives me nuts. This is my own little hobby horse. Mostly because it's like, makes you sound really like you haven't paid attention in a week. When you don't realize that like that circle's not the letter O. And F and G aren't letters, they are variables. Right? Like, it seems like you haven't been listening for an entire long time and you like fundamentally misunderstand algebra. We read that set of symbols as F compose G. All right, let's do some practice on compositions. So here, let's say we have the f of x defined as the function 2x squared minus 3x, and g of x defined as the function negative 3x plus 4. And then we're going to look at a couple of compositions here. So the first one asks us to look at f compose g of x. If I use my definition from above, that's just the same thing as f of g of x. And in the problem, I observe that g of x is just 3 or negative 3x plus 4. So I'll replace the g of x with negative 3x plus 4. And now, when I'm using function notation, what is it telling me to do when I have something written down like f of, something? What am I supposed to do if I have a function notation like we have here where it says f of something, and that something's not necessarily x? Remember, what did we do last class when we had like f of negative x? What did that tell us to do? Replace all the x's with negative x's. So here we're going to replace all the x's with negative 3x plus 4. Exactly the same idea, right? Just following what function notation tells us to do. So if I go and I look at f, I have a 2, and then there's an x squared, and I have a minus 3, and then an x. So where those x's are is where the 3x plus, or negative 3x plus 4 goes. So I'm like plugging the function g into my function f. Does everybody feel okay with what we've done or what we did there? Okay, so at this point the composition is done, but there's still some simplifying that I can do, right? Okay, if I look at this expression, what's the first thing I should be simplifying? What's the first thing I need to do? What? The exponent, right. If you go back to your order of operations, exponents come before multiplication, addition, and subtraction, which are the other operations we see going on there. So the first thing I need to do is do that squaring. How do I square negative 3x plus 4? You FOIL. That's correct. Because what does negative 3x plus 4 squared really mean? Well, it's negative 3x plus 4 times negative 3x plus 4. Is everybody okay there? Okay. Again, easy to forget this stuff. This is all stuff we probably talked about in Algebra 2 or Algebra 1 at some point, but it's been a little bit, so let's kind of walk back through how to do this. All right, so if I look at this piece here, well, I guess so we should, yeah, if I look at this piece here, I have 3 things multiplied together, correct? A 2, a negative x plus 4, and another, or sorry, negative 3x plus 4, and another negative 3x plus 4. Which 2 things should I multiply together first? Well, I have like 1, 2, 3 things, right? Which 3 things should be multiplying together first? Edu? So Edu's saying to do this pair first, right? Does anybody disagree? That's the correct answer, Nick. It doesn't matter, right? You can multiply any 2 things together first. What you want to be careful about is that you don't do this. That's wrong. But whether you multiply the 2 in the first set or the 2 in the second set is fine. I would do neither. I would start by foiling first and then multiplying the 2 through at the end, personally, which is what we're going to do here, but it technically does not matter. Edu. Of course. So again, when we FOIL, we do first 9x squared. Oops. Almost forgot. Got to get that 2 in there. And then outer, negative 12x. Inner, negative 12x. And last, 16. And then we might as well distribute here as long as we're multiplying stuff, right? Notice that I can combine the negative 12x's as negative 24x. And then I'll just distribute that 2 now. So far, so good. Am I done? No. What can I still do? Yeah, combine some like terms. So the negative 48x and positive 9x make negative 39x. And the positive 32 and the negative 12 make a positive 20. There we go. That took a long time, right? That was pretty involved. Are they all going to be this involved? Well, if we think back, really the composition was over at this step, right? The composition didn't take much. It's just how much simplifying is left at the end. And that's going to be really dependent on what your two functions look like, right? Sometimes it might be really quick. Sometimes it might take a minute. But that's okay. Either way is all right. We doing okay here, folks? Not going too fast? Is all right? Okay. I just want to make sure, check in every once in a while. So let's look at the next example. So G compose F. Now, this is just the opposite, right? Instead of doing F into G, we're putting G into F. Should I get the same thing? Right? 2 times 3 is just 3 times 2. Is F compose G just going to be G compose F? Let's find out, right? Let's find out. So G of F of X, and F was 2x squared minus 3x. So everywhere in G, I'm going to replace the x with F. So again, that F went into place of G, or went into the X in G. And now to simplify this is a much easier problem, right? Because there's no exponent involved, there's no foiling to do. I just distribute that negative 3. And look at that, I'm done. But what do you notice about this answer and our previous answer? Are they the same? No. Does that mean we did something wrong? No, we didn't do anything wrong. It just means that you've run into possibly the first operation you've ever seen in mathematics that's not commutative. Right? And by commutative, we mean is the same forwards and backwards, right? Like 2 plus 3 and 3 plus 2. Commutative. They're both the same thing. Here, the order matters. F compose G is not necessarily going to be G compose F. Could it be the same? Yes. What's an easy example where it would be the same? Okay, if they were both the same function, if f and g were the same function, yes, of course, forwards and backwards, they would be the same. That's an easy example. Okay. So far, so good? All right, I think we have one more example on our list here. Let's do that one. This is f compose f of x. So here we have f of x, and we know f of x is 2x squared minus 3x. So I'm going to plug that in to the x's in f. So inside of the first x is going to be 2x squared minus 3x. And inside of the second x is going to be 2x squared minus 3x. Oh, yuckarooskies. Look, we have to FOIL again. I'm going to just do this one FOIL quickly in my head, just in the interest of time. Is everybody okay with that? Okay. And I'll distribute as well. Might as well. Mr. Kulik, how did you do that so quickly in your head? Well, I'll tell you what I didn't do is I didn't actually FOIL this. Right? What I remembered was from my Algebra 2 class. You guys would have talked about your perfect square factoring patterns. I used this formula to go this way, where this is like my A and this is like my B. So I just did 2x squared squared. That's the 4x squared. And I did negative 2 times 2x squared times negative 3x squared. I'm sorry, times 3x squared. And that's my negative 12x cubed. And then I did 3x squared, which is 9x squared. So that's what I did to do that so quickly in my head. If that's something you don't remember, you can still just FOIL that stuff out. Like it's just a little bit of extra time or whatever. It's not the end of the world. Yes, sir. Joey, is that a hand? Oh, okay. Just a little bit extra time. It's not the end of the world, but I am like a busy dude. So if I can save myself a few minutes by using some tool that I remember from a previous class, like giddy up here, I'm going to do that. And then these are like terms. So that ought to be my answer. So far, so good? Okay. Now, composition, maybe you remember doing that last year, maybe you don't. It turns out it's a really important concept because the whole entire idea of an inverse function, or inverses in general, are built around this idea of composition. So let's kind of remind ourselves about that. Again, this is something you should remember doing last year in your Algebra 2 class, but I know that some of us might have had like 3 Algebra 2 teachers at one point last year. So if stuff fell through the cracks and you're just like, yo, it was a big mess for me all year, I get it. That's why we're doing it again right now. Trying to be careful and purposeful while doing it. Certainly, yeah, go ahead. Here we say let f and g be 2 functions. We say that g is the inverse function of f provided that F compose G equals G compose F, and both of those simplify down to just X. In this case, we give G of X a special name. We write it as F inverse. So that's a little notation. Notice that -1 exponent doesn't mean 1 over F. It's just part of the name. You read that as F inverse, not F to the -1. It just is read as F inverse. So what is this really saying? Well, let's say we get like, we have the input x equals 2. And let's say f of 2 is just equal to 6. If I then did f inverse of 6, it should give me back the 2. So what does the inverse do? It's like a map back to your starting place, right? We start at 2, we went to 6. The inverse takes 6 and brings it back to 2. Is everybody okay with that notion? So let's look at finding inverses. And let's start by looking at a mapping diagram. Oops, that's not where I wanted that to pop in. It's fine, I'll move it myself. So here's an example of a function with a mapping diagram. So if I want to draw f inverse, I'm going to draw another mapping diagram. So the values in my domain should be the range values for f, and the value in my range should be the domain values for f. So 4 should go back to 1. 5 should go back to 3. And 6 should go back to 2. And that's what f inverse should do, right? Just kind of following backwards my original mapping diagram. Does that all look okay to everybody? If I look at f inverse here, is this a function?
Yeah.
Yes, right? Every domain gets used, and each domain only goes to one range. Okay. Let's look at a different representation. Let's look at an example where our function is given to us as a set of ordered pairs. So when I read this, what I really want to think about is like what f does. It takes negative 2 to 4, takes negative 1 to 6, takes 3 to 8, and it takes 5 to 8, right? That's kind of what I should be looking at, or what I should be thinking about when I look at that. What would the inverse then need to do? Should take a good 4 to negative 2, 6 to negative 1, and then and then 8 to 5. That's good. That's what my f inverse should do. Let's look at this though for a moment. Is this f inverse a function? Why not?
Because of 8's going to 2 different spots.
Yeah, very good. So we've seen now sometimes our inverse will be a function, and sometimes it's not going to be a function, right? Everybody's okay with that? What we'd want to do is be able to make a prediction about, or a prediction just by looking at f. Can we tell whether f inverse would be a function or not? That's what we'd like to do. To do that, I'm going to introduce some new vocabulary. And we're going to start with 3 terms. The first term is called onto or surjective. The next term is called one-to-one or injective. And the last one is called bijective. We'll talk about what these mean in just a moment. Because again, mathematics E's, sometimes it's not always clear by reading it, like what the heck does that say? Okay. So we say a function is considered onto if every element in the range is mapped to by some element from the domain. In other words, no element of the range is left unused. A function is considered one-to-one if every element in the domain maps uniquely to distinct elements in the range. In other words, no element of the range is used by multiple elements of the domain. And lastly, a function is both one-to-one and onto, then it's bijective. In other words, every element is used and used only once. So everything in the domain is used, everything in the range is used, but each of them are only used one time. I'm going to see a lot of pencils still moving, so I'm going to just hang here for a moment before I go back and point some stuff out. And then we'll continue on and do some examples. Yes. You guys can go together.
Good.
Yeah, you have to use different potties though. Okay. All right. I just wanted to be clear when I said you can go together. What I meant there. don't want anybody to feel uncomfortable like we have to share the same toilet. Which if one person had to poop and the other person had to pee would be quite an act to figure that out. No, I thought that was kind of funny. I thought he'd at least get a giggle. It was very gross, but funny in a high school kind of way. All right. So let's go back and look at these two examples we just looked at. And let's try to determine if these things are one-to-one or onto or both, right? So let's go back and look at the first one. So we're looking at F. Is F onto? Is everything in the range used? Yes. So it's onto. Okay. Is it one-to-one? Is each range used only once? Yes. So we can say then F is bijective, right? So we've seen an example here that as long as F is bijective, the inverse is a function. Do we have to have both conditions, I wonder, to make it? Let's look at our other example here. Let's look at this F. So again, we're looking at the set of ordered pairs. Is this F onto? Well, what's the range of this? 4, 6, and 8, right? Are all of those used? Well, yeah. Okay, so that's onto. Is it one-to-one? No, why not? Yeah. And we see here that F inverse was not a function. So it seems like at least if I don't have this one-to-one property, I can't be a function. We haven't seen an example that's one-to-one but not onto yet. Let's look at a quick example of that. Let's do that. So this is an example here of a function that is, why am I using a different color? Let's just make it all black. This is a function that's one-to-one, but not onto, right? Why is it not onto? Yeah. Now if we do F inverse real quick, is that a function? So is F inverse a function?
No.
Why not?
5 is the range.
Perfect. Yeah, we have an unused domain, right? So it looks like we have to have both one-to-one and onto for F to guarantee that F inverse will be a function. That's our takeaway.
So it has to be, what was the word?
Bijective
Bijective.
is the term.
Subjective. for the inverse.
For the inverse to still be a function. Mm-hmm. So we can analyze, or we can say now, as long as f is bijective, 1-to-1 and onto, f inverse will be a function. Okay, let's continue our discussion here. Let's look at a graph and try to find an inverse from a graph. Okay. So this graph is the function f of x, and we want to find f inverse from looking at the graph. How would I do that? Great, I'm going to use the points. We'll swap the x and y's, and we'll plot those. So 0, -3 is going to become the point -3, 0. 1, -1 would become the point -1, 1. And -2, 5 becomes the point 5, -2. 1, 2, 3, 4, 5, 1, 2. Now, how do I connect these points? Well, the vertex of my function should still be the vertex for my inverse, and the shape of my inverse should still be the same. So it should just look like that. Is everybody okay with how I drew this? Now, you might have also remembered from your Algebra 2 class that we can think about the inverse of a graph as a reflection across the line y equals x. So like if I look at this, get that out of there. If I look at, say, this part of my function, when I reflect it across that line, y equals x, I get like this part of my inverse, right? I think this is hard to see, but it's a nice check after you've drawn your function, your inverse, like drawing that line y equals x to make sure it's like, okay, that looks like a nice, like it's reflected across. I think it's much harder to go from the graph and then reflect across that line because it's diagonal. But once you've drawn your function, your inverse, if you draw that diagonal through there, it's a nice check at the end to make sure everything is in the right place. That's how I like to use it. So far, so good. Okay. So if I look at f here, in this last example, is f 1-to-1 or onto? Well, actually, right away we notice that f inverse is not a function, right? Everybody agree with that? So what part of the bijective did f fail? Is it not 1-to-1? Is it not onto? Is it not both? You did. It's the one-to-one part.
50, so.
Yeah, it is a 50-50. So
Shooter's gonna shoot.
it turns out that F is not one-to-one. How can we look at this graph and tell? Well, if I look, this point is the point 2, 5, right? This is the point 2, -5. What do I notice? Repeated y coordinate, right? I notice also those 2 points lie on the same horizontal line. So I can check a graph for one-to-one by just doing a horizontal line test. So let's define what we mean by horizontal line test. So we say the horizontal line test defines y as a one-to-one function of x if and only if there is no horizontal line that intersects the graph at more than one point. So what do we have here? HLT will tell you if f is one-to-one, which will tell you if f inverse is a function, right? So really I can use that horizontal line test on f to check if f inverse is a function. How are we feeling so far? Still doing good? Pace is good? Okay. Trying to make sure we're going slow and being very careful how we're doing this and like building this out in a way that seems like it makes sense, like I'm laying all the breadcrumbs down and like building one idea to the next, to the next, to the next. So everything should feel nice and connected, which is what I'm hoping for. Remember when we talked earlier, there was like 4 ways of representing a function, right? We've talked about how to find the inverse when we have a mapping diagram, a set of ordered pairs, a graph. The last representation is an equation. This one we're going to do a lot of examples of because the algebra can be quite different depending on what your f looks like. And we're just going to do one example today, and next class we'll continue on and do a bunch more examples. So here we're going to be finding the inverse for the function f of x equals 3x minus 7 algebraically. So this is the process we're going to use, and the process is the same every single time. The algebra that we need to use to accomplish that can be very different depending on what the function looks like, but the process is always going to be the same. So what I'm going to do is I'm going to begin by rewriting the f of x as a y. And then I'm going to use algebra to get the x by itself. So in this case, what would I do first? Add 7. I would not want to divide yet.
What are you saying?
I mean, you could, but you have to be really careful on how you do that. And after we've added 7 to both sides, next thing we do is, now we'll divide by 3. Okay. So now the x is by itself. What I do next is I'm going to swap the names of my variables. So everywhere I had an x, I'm going to write y, and everywhere I had a y, I'm going to write x. Remember when we found our inverses before, we just swapped the x and y coordinates? Remember doing that? This is me doing that here algebraically, right? And now this is my inverse, so instead of writing it y equals, I'll write it f inverse is equal to x plus 7 over 3. Joey.
Could you write it like 1/3 x plus 7/3?
Absolutely. Yes, absolutely. You could write it that way as well. They're equivalent statements. I give no, like one is not preferred over the other. I like writing it this way because it's a little less writing. I only have to write 1 3 instead of 2 3s. But they are the same thing and would be accepted equally. We're going to stop right here for today. At this point, I'm going to assign the last part of the chapter 1 problem set. Keeping in mind, you probably can't complete this whole problem set at this point because, well, we have still a bunch of examples left to do, but it's a big final section. It's 25 to 56, so that's a lot of problems, so I want to give it to you early. Right now, you should have no problem doing up until 43. So up to 43 should be no problem at this stage. Also, as a reminder, for Sunday, we have due the rest of the 23 through, no, it's 19 to 25, right? Or 24? 19 to 24 is the problem set for Sunday. You also have the delta math, right? That was due Sunday. At this point now, you should be more than comfortable finishing any problems on the delta math. We've done enough now for you to determine if something's an inverse or do a horizontal line test or something on it. We talked about all those ideas. So those two things are due Sunday. And then 25 through 56, I would suggest getting a little bit of a start on so you're not like scrambling, try to do 10 or 10 or so of those problems just to get some stuff knocked out before next week so you don't have to try to get 30 homework set problems and all that jazz done, in a week, which is kind of tough. Pick away at it, right? Do a little bit every day and then it feels less of a daunting task. You spend 20 minutes a day doing it instead of like, I spent an hour and a half on math homework today. It's like, well, it's rough. Absolutely.
May I?
Yeah.